So we just finished talking about glomerular filtration, and now we're going to move on to the second basic renal process, which is tubular reabsorption. And we're going to pay particular attention to the importance of sodium reabsorption in the kidneys, because sodium reabsorption is we invest a lot of energy into it because through the process of sodium reabsorption, we accomplish a lot of other tasks. Okay, so going back to this basic renal process conversation, we talked about glomerular filtration, right? We talked about how about 20% of the plasma that enters the glomerulus gets filtered, right, into the Bowman's capsule. And the other 80% that didn't get filtered moves on to the peritubular capillaries. Now, glomerular filtration, as you recall, was a passive, totally non-selective process. So the composition of plasma and the filtrate is identical minus the proteins in the cells. So there's a lot of things that we filter that we really want to take back. And tubular reabsorption is an opportunity for us to take back these things that we don't want to excrete, that we filtered but we don't want to excrete. Now, unlike glomerular filtration, tubular reabsorption can be passive, it can be active, okay, depending on the substance, but it is always selective. So tubular reabsorption can be passive, can be active, but it's always selective. We're very selective in what we reabsorb. Okay, so the process of tubular reabsorption means we're moving from the interior of the tubule, right, the tubular lumen, across the epithelial boundary of the tubule and into the plasma. Okay. Now, there are epithelial cells that line the renal tubule, that line the nephron tubule, and epithelial cells, like all other epithelial cells, they're composed of these cells with very tight junctions between the cells, so that normally substances need to move through the cell when they want to cross this wall. So they have to cross two plasma membranes. So these numbers represent spaces that need to be crossed in order for something to be reabsorbed, in order to move from the tubular lumen into the peritubular capillary. So the first barrier is what we call the luminal membrane of the tubular cell. Okay, so the luminal membrane has to get crossed. Then number two, that substance has to diffuse across the interior of the cell. And then number three, it has to cross the what's called the basolateral membrane. Okay, and the basolateral membrane is actually composed of two parts. There's the basal membrane, right, which is this space over here, and then there's the lateral membrane, that's this space over here. So it can either cross the basal side or the lateral side, okay, but it's got to cross the second membrane. And then in number four, it's got to diffuse across the interstitial fluid space. And then number five, it's got to get across the capillary wall. Okay, we reabsorb quite a lot. Okay, so we reabsorb quite a lot. For example, about 99% of the water that is filtered at the glomerular capillaries gets reabsorbed. 100% of the glucose is normally reabsorbed, and about 99.5% of the sodium that's filtered gets reabsorbed. So we reabsorb quite a lot of things. So sodium reabsorption is an important event that happens in the kidneys. Sodium reabsorption is done through an active mechanism, meaning that we have to expend energy in order to reabsorb sodium. about 80%, and it's quite a lot of energy because about 80% of the energy requirements of the kidney is actually used for sodium reabsorption. Now, the reason why the kidneys can justify such a huge input or investment of energy is because sodium reabsorption is coupled to or allows for the movement of many, many other substances. So sodium reabsorption is really not just an end. So we do have to reabsorb sodium, but sodium reabsorption is also a means for accomplishing the transport of many other substances. Okay? And sodium reabsorption is done throughout most of the tubule, and it plays an important role throughout the tubule. Okay? There's only one part of the nephron where sodium is not reabsorbed, and that's through the descending loop of Henle. Okay? So the descending loop of Henle is the only part of the nephron where you see no sodium reabsorption. Okay. So sodium reabsorption plays a really important role in every part of the tubule. So in the proximal tubule, it plays a critical role in the reabsorption of glucose, amino acids, water, urea, and several other substances. Okay? And we'll talk about more of that in a moment. In the ascending loop of Henle, it plays an incredibly important role in the kidney's ability to concentrate urine and conserve water. In the distal tubule and the collecting duct, sodium reabsorption is actually under hormonal control, and it plays a role in regulating ECF and plasma volume and blood pressure. Okay, so very big job for this little electrolyte. Okay, so the general pattern, the general mechanism for sodium reabsorption in the kidneys occurs this way. So sodium has to first get across that luminal membrane, and it has to get across that basolateral membrane. Those are the big barriers. So in general, depending on where you are along the nephron, sodium tends to cross the luminal membrane either through a passive channel, okay, or through some sort of co-transporter. Now, remember, this is the process of sodium entering a cell. So it's very easy to get sodium to enter a cell. It has a huge driving force to get in. Okay, so allowing the cell to passively let sodium in is very easy to do. You just have to provide it a channel. But through multiple parts of the kidney, we actually exploit this big driving force for sodium to get across by linking it in a co-transporter so that we can actually harness the energy of sodium entering the cell in order to either actively move a substance in or out of the cell. Okay, so that's really where, at least on the luminal membrane side, we're going to really use sodium to our advantage. So now that we have sodium inside the cell, it's going to be harder for us to get sodium to leave the cell. So sodium crosses the basolateral membrane through the sodium-potassium ATP pump. Okay. So throughout the renal tubule, when sodium is getting reabsorbed, it's crossing the basolateral membrane by the use of these ATP pumps. And it's this step that is what costs so much energy. Okay? Once it gets across, sodium then can diffuse across and get into the peritubular capillaries. Okay, so the first part of the nephron after Bowman's capsule is the proximal tubule. Now the proximal tubule is a part of the nephron where a lot is going on. There are a lot of things happening at the proximal tubule. A lot of reabsorption events, a lot of secretion events, and it's where we make major adjustments to the composition of urine. Okay? So right after we've filtered urine, that urine enters the proximal tubule, and we adjust the composition significantly. Okay? So there is a lot of sodium reabsorption going on at this proximal tubule. Now, one of the ways that sodium crosses the luminal membrane of the proximal tubule is through a co-transporter with glucose, amino acids, and water-soluble vitamins. So at the luminal membrane in the proximal tubule, we have sodium glucose co-transporters, sodium amino acid co-transporters, sodium vitamin co-transporters. So as sodium moves downhill into the cell, we use that energy to pump glucose, amino acids, and vitamins into the cell. Once sodium is across, it gets across the basolateral membrane through the pump. And once glucose, amino acids, and the vitamins get across, they cross the basolateral membrane through a passive facilitated diffusion carrier. Okay? And then diffuse into the peritubular capillary. So the reabsorption of glucose, amino acids, and the vitamins are highly dependent on sodium reabsorption. Okay? And this is all happening in the proximal tubule. Now, if we look for a moment, a little closer look at glucose. Now, glucose got filtered at the glomerulus. So glucose got filtered at the glomerulus, but if you look at a healthy person's urine, you see no glucose. Okay? You shouldn't see glucose in a healthy person's urine. That's because normally 100% of the glucose that got filtered is fully reabsorbed at the proximal tubule through this mechanism. Okay? However, for some people who are diabetic, where their blood glucose gets very, very high, you actually can start seeing glucose in the urine. Okay? So that means that there's a limit to how much glucose your proximal tubule can reabsorb. Okay? So normally, we can handle the amount of glucose that gets filtered. It's a concentration of glucose we can easily reabsorb. But as the glucose concentration of the blood gets higher and higher in a diabetic, this transport mechanism, right, starts to get towards its saturation point. Okay? Meaning the rate at which we can reabsorb glucose is ultimately limited by the number of available transporters, both at the luminal membrane and at the basolateral membrane. Okay? If the concentration of glucose in blood, and therefore in the filtrate, is too high, then we start to hit the limit. We start to run out of available transporters, and we're reabsorbing glucose as fast as we can, but it's not enough, and some glucose remains in the urine. Okay? And that's where you see it when you do a urinalysis of someone with hyperglycemia and diabetes. So for these substances that are reabsorbed through mechanisms that use transporters, we have this concept called a tubular maximum. Okay? The tubular maximum is a rate, which is very important to keep in mind. The tubular maximum is a rate. It represents the maximal, so let's use glucose as our example. Tubular maximum is the maximal rate of glucose reabsorption. Okay? And that it's limited by our available transporters. Okay, so for glucose, let's look at what this tubular maximum looks like. So for a normal plasma glucose concentration, which is about 100 milligrams per 100 milliliters of plasma, okay, if we look at the at that concentration, we are able to reabsorb 100%. So how fast are we filtering glucose if our blood concentration is 100 milligrams per deciliter? So if we multiply our plasma glucose concentration times our GFR, right, a normal healthy GFR is about 125 mils per minute. So 100 milligrams per deciliter times 125 mils per minute. We are filtering glucose at a rate of 125 milligrams per minute. Okay, that's the filtered load. The amount of any substance filtered by the kidney per minute. That's the filtered load for glucose at a normal blood concentration for glucose. So we can easily handle that. In fact, the tubular maximum for glucose is actually 375 milligrams per minute. Okay? So we're normally filtering 125 milligrams per minute, but we would be able to handle if we started filtering at 375 milligrams per minute. Anything more than that, and we can't handle it, it's going to stay in the urine. So the question is, this is our maximal rate of glucose reabsorption. At what plasma concentration, how high does glucose have to be in order to force us to our tubular maximum? Okay. So the plasma concentration, the maximal plasma concentration for glucose that pushes us to our tubular maximum, that's a measure that we call renal threshold. Okay. The renal threshold is the maximal plasma concentration of any of these organic nutrients, including glucose, right? That above that concentration, you start to see it in the urine. Okay. So if we look at our tubular maximum, which is here, 375 milligrams per minute, and remember the way that we did this in the last slide is we took GFR. Okay, this is GFR. Okay. And then this is our TM, this is our tubular maximum. And so before, what we did is we took plasma concentration times GFR to get our filtered load. So the renal threshold is actually 300 milligrams per deciliter. So this 300 milligrams per deciliter is our renal threshold. So renal threshold times GFR is tubular maximum. Okay? So any blood concentration above 300 milligrams per deciliter is going to result in glucose remaining in the urine. Okay? Now this is really important because you notice that normal plasma concentration was 100 milligrams per deciliter, right? And the renal threshold is 300 milligrams per deciliter. So glucose can increase by a factor of 3. It can triple before you ever see glucose in the urine. Okay. So because that's true, because the renal threshold is so much higher than the normal concentration for glucose, we know that the kidneys aren't playing an active role in regulating blood glucose. Okay? The renal threshold is set too high. And so when you do see glucose in people's urine when they're diabetic, that means that their blood glucose is actually very, very high. Okay? It's at least 3 times normal. Okay, so Moving on, so that was the pattern in the proximal tubule. Moving on down the nephron, this pattern of sodium reabsorption in the ascending loop of Henle, okay, and this is not critical for understanding sort of the big picture stuff, but the pattern of reabsorption of sodium at the ascending loop of Henle, sodium is crossing the luminal membrane through a cotransporter with potassium and chloride. And then once across, potassium is passing through a passive channel, and chloride is also passing through a passive channel. And sodium is crossing the basolateral membrane through the ATP pump. Okay. If we look at the distal tubule, sodium crosses the luminal membrane through a cotransporter with chloride. It crosses the basolateral membrane again through the pump, and chloride crosses through a passive channel. And then finally in the collecting duct, it's actually the most simple mechanism. Sodium crosses the luminal membrane through a passive channel and then crosses the basolateral membrane through the pump.